Okay, in the last video we talked about the physical meaning of the heat equation. In this equation we're going to try and actually solve it. Okay, so this is the differential equation and boundary conditions we got in the previous video. Now I'm going to try and use the strategy of separable differential equations to try and solve it. So our strategy is to use u equals a function of x times a function of t. So our differential equation, k second derivative of u with respect to x equals derivative of u with respect to t is going to turn into derivative of this with respect to x twice is going to be x double prime times capital T, and derivative with respect to t is going to be x times capital T prime. And as we mentioned in the previous section, we're using capital X as a function of little x, capital T as a function of little t. Okay, so I want to now solve it. If possible, keep everything in standard form. So I'll divide everything by kt. And might as well go ahead and divide by x as well. So the x cancels, kt cancels, and we get x double prime over capital X is equal to t prime over kt. Okay, this is a function of x only, this is a function of t only, so they have to be a constant. You can't have a function of x equals a function of t. So we use minus lambda as our constant to make our next step a little bit simpler. When I write it as two equations, x double prime over x equals minus lambda, t prime over kt equals minus lambda. We can then multiply both sides by the denominator. And move it to the other side. And conveniently, since we started with a minus lambda, we end up with a positive, all positive terms on the left-hand side. Or when I rewrite my differential equation in standard form, we have no fractions and no negative signs. Yay. Technical difficulties on 2 videos in a row. Not the same cat. Okay, so anyway. We've now successfully separated the differential equation. Theoretically, you might think, oh, he's done with this video. Nah, not quite, because I also have to think about what happens to these boundary conditions. So let's actually go back and look at the boundary conditions as well and see what's going to happen to them. Okay, so this condition says that you're holding little x equals 0. So that means if I replace u with capital X, capital T, that means capital X of 0, capital T of t is equal to 0. And that's for any t. Okay, well, this is a constant times a function is equal to 0. If we have a constant times a function is equal to 0, either this constant is 0 or this function is always 0. If this function was always 0, we'd have u as 0. Okay, so probably that's not what we want to have happen. If capital T is always 0, make my x now look like my t, then we're just going to get the trivial case for our u, because we're going to have x times 0, which is going to be trivial. So probably it's this thing. So this is going to be our boundary condition, or one of our boundary conditions, and notice it actually kind of nicely goes with that one. Okay, let me get a new piece of paper. If I look at the second boundary condition, which is this u of lt equals 0, is going to be essentially the exact same. Capital X of L times capital T of t is equal to 0. So either x of L is 0 or capital T of t is 0. And again, if you think about it, this is a constant equals 0 or a function being 0. If the function is always 0, that's going to end up meaning that u of xt is 0. Probably that's not what we want to have happen, so I guess our boundary condition is going to be this one instead. And last but not least, u of x0 equals f of x. Let me make sure I'm still in the video. Okay. Same thing. Capital X of x times capital T of 0 is equal to f of x. And I'm not going to mess with this too much because what we're probably going to have to do is figure out what T of 0 is. I can't split this up into cases just because the product equals something doesn't mean that one of the parts is that. But I will point out that T of 0 is going to be a single number, which is a constant. And so essentially that means that there's a close relationship between our capital X and our f of x. So I'll just leave this one for now. I won't really get into this. But if I summarize what we got as our answer, we have two differential equations. One that involves only x's, and one that involves only t's. And then we have this extra constraint that we don't know what to do with. Okay, so what that means is we have a differential equation in terms of x with boundary conditions, so we should be able to actually solve this one all the way through. And then we at least have some way to get started on this one. We might want to do the x first, since we do have both of the initial conditions we need to solve a second order differential equation.